Hello, and welcome to this GeoStudio Tech Talk, which is the first session of a two-part series on heat transfer in a complex geological setting. I'm Catherine Dampierre, and I work with the GeoStudio engineering team here at Sequent. Today's webinar will be approximately 35 minutes long. Attendees can ask questions using the chat feature. I will respond to these questions via email as quickly as possible. A recording of the webinar will be available so participants can review the demonstration at a later time. GeoStudio is a software package developed for geotechnical engineers and earth scientists, comprised of several products. The range of products allows users to solve a wide array of problems that may be encountered in these fields, including stability analysis, the movement of water, contaminants, air, and energy through the ground, and stress and deformation in soil and rock. This webinar series will focus on 3D geometry creation in GeoStudio, as well as our 3D heat transfer analysis product, Temp3D. Let us start by considering the project location. Here you see the regional geology of our project site in central Alaska, including river valleys and a roadway. The geology is complicated by faults, one of which is visible on the side of the domain. A new building is to be constructed on this plateau. To simplify our workflow, we will use only a small portion of the regional geology for our GeoStudio analysis domain. The top brown material in our domain represents an ice-rich silt. The top portion of this can be considered an active layer where temperatures fluctuate above and below freezing over the course of a year. Below the active zone is continuous permafrost. Permafrost is a layer on or under the ground surface comprised of soil bound together by ice that remains frozen for at least 2 consecutive years. Below the permafrost is unfrozen ground. However, in this case, we will see that our domain remains frozen to the bottom. Constructing man-made structures on permafrost, including buildings and embankments, is challenging. Heat transfer from a building can melt permafrost, causing subsidence of the ground surface, among other environmental challenges. Thus, great care must be taken when building in Arctic regions where permafrost is present. In some cases, buildings are constructed on piles to minimize their influence on the underlying thermal regime. However, this type of construction is not always practical. Buildings constructed as slab-on-grade must employ other techniques to minimize thermal impacts. One of these alternative techniques is the installation of thermosyphons. A series of thermosyphons was installed alongside this airport terminal building. Thermosyphons reduce the thermal impact of a building by removing heat from the ground. Let us review how a thermosyphon works. Two-phase thermosyphons are passive heat exchangers that maintain frozen ground conditions by circulating a fluid without the need of a pump. The circulating fluid is generally pressurized carbon dioxide or ammonia, which vaporize when heated and condense when cooled. This fluid is contained in a closed and sealed vessel that consists of an evaporator, which is below the ground, and a condenser, which is above the ground surface. In the majority of cases, the evaporator is sloped to ensure that the condensate flows toward the lower portion of the evaporator. The fluid in the evaporator vaporizes as it extracts heat from the ground. Then it rises up the vessel into the condenser, where it cools, condenses, and returns below ground. This cycle continues while the air temperature remains below a user-specified value, generally set equal to the freezing point of pure water, and the difference between the surface and air temperature is greater than a user-specified value, typically set equal to 1 degree Celsius. Note that this process should not be confused with open processes in which the fluid is simply released into the atmosphere after extracting heat from the ground. In the case of two-phase thermosyphons, the loop is closed, and the same fluid continuously travels from evaporator condenser and back. Our project site includes two-phase thermosyphons like the one shown here for mitigating the impact of our building on the underlying permafrost. To model thermosyphons in GeoStudio, a line or cylinder is added to the project geometry to represent the evaporator. The thermosyphon boundary condition available in TempW and Temp3D can be applied to this line or cylinder and computes the convective heat flux associated with the entire thermosyphon system. Let us review the project in greater detail before starting our work in GeoStudio. At our project site, we will conduct a three-dimensional analysis to investigate the effect of a series of sloping thermosyphons installed below a 10 by 10 meter insulated slab-on-grade building. In this image, you can see the footprint of the building foundation relative to the overall domain. Here is a cross-section of the building foundation. The building lies on 0.25 meters of extruded polystyrene foam insulation, overlying 1.5 meters of non-frost susceptible gravel. 3 thermosyphons are installed in the gravel portion of the foundation, with a spacing of 3.33 meters on center. The position of one of these is visible in this cross-section. The thermosyphons are sloped 3 degrees from a horizontal reference. They are 9.51 meters in length, 88.9 millimeters in diameter, and are 1 meter deep on average. Each thermosyphon evaporator is connected to a 6.5 square meter condenser. The condenser is not included in the model domain as the thermosyphon boundary condition accounts for the whole thermosyphon system when applied to just the point, line, or cylinder representing the evaporator. This is what we want to model in GeoStudio, but what steps are necessary for conducting this type of analysis? Let us review the modeling procedure, which we will follow in this webinar series. When setting up finite element numerical analyses in GeoStudio, we always suggest the following steps. Create the model domain by setting up your geometry. Define the project physics by adding analyses to the project file and defining the material properties associated with the model geometry for each of the physical processes selected for the project. Define the boundary conditions or the external forces acting on the domain. Generate and refine the finite element mesh with smaller mesh in areas where higher gradients are expected. Solve the analysis to determine the value of the variable, in this case temperature, over the entire domain for all time steps. And finally, verify or interpret the results by interrogating the model. In the first part of this webinar series, we will focus on the first step of the presented numerical modeling procedure and create the three-dimensional model domain associated with our project. The remaining steps will be covered in Part 2 next month. Before opening GeoStudio, let us review the steps we will take to generate the 3D geometry. The three-dimensional geometry will be created using GeoStudio's 3D geometry creation tools with inputs from a Leapfrog geological model. First, I will create a rectangular prism using the Sketch and Extrude tools. To establish the ground surface, I will first import the topographic surface from my Leapfrog model. To do this, I use the Import Background Mesh option and select my Leapfrog file from the central server. I will then fit a 3D surface to the imported background mesh and use this surface to cut and remove the portion of the rectangular prism above the ground surface. We now have our overall model domain. However, there are additional details we must add. The subsurface is comprised of multiple materials. In a 3D GeoStudio analysis, there are 2 methods for defining the stratigraphy. The first is to import surfaces representing the contacts between the subsurface materials. In this project, I will import a contact surface from my Leapfrog project via Central using the same method as when I imported the ground surface. I will fit a surface to the corresponding background mesh and use this surface to cut the model domain. The portion of the domain above this contact surface represents the ice-rich silt. Below this contact surface are multiple units. However, due to faulting, the contacts between the units cannot be represented by a parametric surface. Thus, I will use a different method to define the subsurface materials in the bottom portion of the domain. To do so, I will import the geological model volumes from my Leapfrog project, again via Central. These geological model volumes can be used during the meshing process to assign materials to elements. I then will add the building foundation to the domain by extruding a sketch of the building footprint and cutting this from the subsurface domain. Finally, cylinders representing the thermosyphon evaporators are added by extruding circles along an angled path and cutting this from the building foundation. Let us now open GeoStudio to start our work on this project. I've opened the latest version of GeoStudio and will set up a new project file using the metric unit system. In the Define Project dialog, I will start our geometry definition by adding a three-dimensional geometry to the project tree. I can now start creating the associated geometry items. Since our project site represents a small portion of the larger geological model, let us start by bringing in the geological model volumes from our Leapfrog model. This step is not necessary for creating our geometry, but will help us set up our model domain relative to the larger area. To do this, I will select the Import icon in the top toolbar of the 3D view and go to Import Geological Model Volumes. A dialog opens allowing for the selection of the corresponding Leapfrog project, which is stored on Sequence Online Data Management Solution called Central. I will select the central server my project is stored on, the project name, branch, ID, and the geological model I wish to import the material volumes from. GeoStudio uses a right-handed Cartesian coordinate system, assuming that the positive y-axis is upwards. Leapfrog uses a different coordinate system. This means that I need to remap the original coordinate system to our GeoStudio coordinate system. I can do so using the Remap Axes portion of the Import Geological Model Volumes dialog. Here I will remap the x-axis to the z-axis, y to x, and z to y. I will also press the Adjust Base Point button so that the minimum point of the imported geometry is placed at the origin in 3D GeoStudio space. When I press OK, a dialog opens to see if I wish to save these transformation settings. I will select Yes so I can use the same transformation settings when importing other project elements in future steps. We now see the entire regional geological model in our 3D space. The imported geological model volumes are shown at the bottom of the Geometry Explorer list. Note that these volumes are not part of the 3D geometry in the file, as there is nothing in the geometry portion of the list. However, we can use them for assigning materials to the domain during the meshing procedure, which we will do at a later stage. I will now start to create my 3D geometry by focusing in on this plateau. First, I will create the rectangular prism by sketching a square on the XZ plane. I will select this plane and then go to the Sketch 2D icon in the top toolbar. The view shifts so I'm looking down on my geological model. I will select the Line Sketch tool and draw a rectangle. I will then use the Select tool to click on each point and modify the relative coordinates. I will then edit the plane of the sketch by pressing the Edit Plane button and changing the offset to 300 meters. This means that the sketch is on a horizontal plane, 300 meters above the axis. Now that I've positioned the base of my 3D domain relative to the larger geological model, I will select all the geological model volumes and change their visibility. This allows me to better see the components of my 3D domain. I will also rename the item in the design history to Domain Sketch, so others opening this file can follow the steps that I used to generate the 3D geometry. To generate a rectangular prism from the sketch, I will extrude it. I will right-click on the sketch, then go to Extrude. In this dialog, I will edit the automated generated slice so it is 800 meters from the sketch plane. After pressing OK, you can see that we now have a 3D solid in our model space. I will rename this step Domain Extrude. The next step for creating the geometry is to cut the rectangular solid by the ground surface. To do so, I will import a background mesh representing the site topography. I will go to Import, Background Mesh, and select the From Central option, as I wish to bring in the topography from the same project file as I imported the geological model volumes from. I will use the transformation template that I had previously saved to remap the coordinate system. You will notice that this brings in the topography associated with the larger regional geological model. We'll now fit a surface to the topography as this was imported as a background mesh, and so it is not a 3D geometry item. I'll click on the Fit Surface icon and select To Background Mesh. In this dialog, I must specify the background mesh that I wish to fit a surface to. Then I will adjust the surface parameters to increase the surface resolution and the flexibility of the surface. I will press OK when I have adjusted the parameters to the desired values. I will rename this step Topography Fit Surface. I can now see both the background mesh and the fitted surface in the 3D view. I will turn off the visibility of the background mesh to better view the 3D surface that was generated. This surface will now be used to cut the original rectangular prism in two. I will select the Cut icon and specify the topographic surface under Bodies A, as this is the cutting body. For Bodies B, I will select the rectangular prism, as this is the body I wish to cut. I will then select the Split Cut option such that the topographic surface beyond the prism is removed. Once back in the main 3D view, I will rename the step Topography Cut. The original prism is now divided into two solids. We must remove the top solid that is above the ground surface. To do so, I will go to the Delete Bodies command and select the top solid. After pressing OK, I will rename this Topography Delete Body. We are done creating the overall model domain for the subsurface. Now we must divide this into different solids representing the various subsurface materials. As previously mentioned, we can import contact surfaces to cut up the domain. I will use this method for dividing the top portion of the domain. To do so, I will follow the same steps as when I imported the ground surface. Again, I will select Import Background Mesh from Central and specify the same project file as before. I can use the Save Transformation template to update the coordinates. A second background mesh appears in the Geometry Explorer. We will now fit a surface to this mesh by selecting Fit Surface to Background Mesh, specifying the contact surface we just imported, and adjusting the surface parameters. As before, we will turn off the background mesh now that we have used it to generate a 3D surface. I will rename this step Contact Fit Surface. Now we cut the domain using the surface. In the Cut dialog, the contact surface is added to the Bodies A input, and the solid representing the subsurface is specified under Bodies B. As with the ground surface, we will use the split option so the contact surface outside of the subsurface solid is removed during the cut operation. I will rename this step Contact Cut. The portion of the domain above this contact surface represents the ice-rich silt. Below this contact surface are several materials. To demonstrate an alternate method for dividing the subsurface, I will use the geological model volumes to assign materials to the bottom portion of the domain. To do this, we simply need to import the geological model volumes, which we have already done, and associate the geological model volumes with this portion of the domain. To do so, I will select the bottom solid. In the Properties window, I can see that no material is assigned in the drop-down menu. However, the geological model volume materials are all associated with the solid. This means that during the meshing process, each element is assigned one of the materials from the geological model volume based on its location. If I were to quickly generate the mesh now with 5-meter hexahedral elements, you will see that materials have been assigned to the elements from the geological model volumes, and a fault lies within this bottom region of the domain. Faulted subsurface domains are difficult to cut into discrete solids using the first method I demonstrated, by bringing in contact surfaces as background mesh and fitting a parametric surface to them in GeoStudio. However, the second method demonstrated here, using the imported geological model volumes, can be used in many cases as an alternative. We are now ready to add the building and thermosyphon details to the model geometry. I will go back to the geometry view and start by sketching the building footprint. To do so, I will select the XZ plane and go to the Sketch 2D command. I will select the line tool and draw a 10 meter by 10 meter square in the center of the domain. I will then go to Edit Plane and define the offset to be 431.2 meters, which is equal to the highest topographic point within the building footprint. I will rename this sketch Base Sketch. To use this sketch to create the polystyrene insulation and gravel, I will right-click the Building Footprint sketch and select Extrude. I wish the footprint to be extruded down from the sketch in the negative Y direction. I will select the Reverse option in this dialog. Then I will edit the automatically generated slice at 1 meter so it is at 0.25 meters, as this is the depth of the insulation. I will then add another slice at 1.75 meters, since the gravel is 1.5 meters thick below the insulation. After pressing OK, I will rename this step Base Extrude. I will explicitly cut the solids representing the gravel and insulation from the original subsurface solid. I will select the two solids representing these materials from the geometry list in the Geometry Explorer and then press the Cut icon. These two solids populate the Bodies A entry box. I wish to cut them from the larger domain, so I will specify this solid for Bodies B. I will select the Cut option, press OK, and rename this step Base Cut. The final step for setting up our geometry is to add the solids representing the thermosyphon evaporators. I will select the Sketch 3D command and use the Line tool to draw a line. I will modify the endpoints of the line. This line represents the angled path of the thermosyphon evaporator. I will rename the sketch Thermosyphon's Path. To create the cylinders representing the thermosyphon evaporators, I will first create a sketch plane to draw the circular cross-sections on. To do so, I select the plane icon and use the Plane from Point on Line construction option. Then I will click on the point at the end of the line representing the thermosyphon evaporator path. I will rename this step Thermosyphon's Plane. I now will create a 2D sketch on this plane representing the circular cross-section of the thermosyphon evaporators. I will right-click on the plane and select Sketch 2D. In the sketch view, I will draw 3 circles, one at the origin, one to the left, and one to the right. Using the Select tool, I will modify the radius of each circle to be 0.04445 meters. I will modify the position of the left and right circles so they are 3.333 meters away from the central circle. This leads to the same contributing surface area for each thermosyphon. This step will be renamed Thermosyphons Sketch. To create cylinders from the sketch, I will right-click it and select Extrude. I will edit the automatically generated slice to represent the length of the thermosyphons, which are 9.513037 meters long. This generates 3 cylindrical solids. I will rename this command Thermosyphons Extrude. I now will explicitly cut the thermosyphons from the domain. To do so, I will turn off the visibility of the solid representing the ice-rich silt. Then I will select the 3 cylindrical solids representing the thermosyphon evaporators in the geometry list and press the cut icon. The 3 cylindrical solids automatically populate the bodies A input. I will select the split cutting option and specify the solid representing the gravel portion of the basement foundation as the bodies B input. The 3D geometry representing the subsurface, future building foundation, and thermosyphons is now complete. In part 2 of the webinar series, we will continue our work on this model by adding analyses to the project file, defining material properties and boundary conditions, refining and generating the finite element mesh, and interpreting the 3D results. This concludes our webinar on generating the three-dimensional geometry for a heat transfer analysis. As we've learned today, elements from a Leapfrog project can quickly be imported via Central and used to assist with generating the 3D domain. We also demonstrated 2 methods for dividing the subsurface, as well as the wide range of tools available in GeoStudio for creating 3D bodies or elements. Resources related to this webinar are available online. An online Build3D course is available through the Sequent Learning portal. The only thing required to take this course is a Sequent ID, which can be created for free. Multiple 3D example files can be downloaded from the GeoStudio website at geoslope.com. To learn more about GeoStudio, there are also many tutorial videos, example files, engineering books for each product, and past webinars available on the GeoStudio website. And finally, we have 4 upcoming in-person workshops in London, Vancouver, Denver, and Brisbane. For more information, head to our website. We've now reached the end of this webinar, but you can register for the second part of the webinar series taking place next month. A recording of this webinar will be available to view online. Please take the time to complete the short survey that appears on your screen so we know what types of webinars you're interested in attending in the future. Thank you very much for joining us, and have a great rest of your day. Goodbye.